All right, so today we are going to be learning about stoichiometry. And first off, I want you to open up to page 1 of your unit book so that we can get an idea of what stoichiometry even is and why is it different than something that we've already worked on. So when you open up to page number 1, there are 3 completely worked stoichiometry problems for you. What I would like for you to do is after I finish talking, pause the video, and I want you to look through and think about all that you already know how to do and find the one new step in our stoichiometry problems that's different than what we've done in any of our other units. So go ahead and pause your video. Okay, so I hope that after pausing the video, you see that we still can put starting and ending amounts in boxes, label our starting and ending amounts, just like we've done with every word problem that we've ever worked. The first step in number 1, it says how many grams of sodium sulfate will be formed when you start 200 grams of sodium hydroxide. First thing you should know how to do is write and balance the chemical equation that's up top there. That's a double replacement reaction. In Unit 7, we learn how to convert from grams to moles using mole island. And so I see 2 of those gram to mole conversions, but then in the middle, I see one new piece, the mole to mole ratio. Okay, the next problem, I again have another chemical reaction that you guys can and should be able to write. It's a synthesis reaction. A grams to mole, a mole to mole, a mole to gram. So again, there's that new piece, the mole to mole ratio. Even on number 3, you can see the scratch work where the chemical formula was written using Unit 5 nomenclature. So KClO3, potassium chlorate, decomposes into potassium chloride and oxygen gas. You can write and balance the equation. This time we were given atoms of potassium chlorate, and there's Avogadro's number like you used in Unit 7, and then again a mole to mole ratio. So the big takeaway that I want you to see from this page is that now we are going to be using a mole to mole ratio. If you can, take a look at where the mole to mole ratio comes from. And the mole to mole ratio is coming from the coefficients of your balanced equation. The coefficient matches up with the compound that's on the compound that it's next to in the problem. All right, so stoichiometry, to answer the starting question, what is stoichiometry? It's the mathematics of chemical reactions. The mathematics of chemical reactions are, we're able to use a gram to mole conversion, our mole to mole ratio, to change from one compound to another. In stoichiometry, I'm able to calculate how much product can be produced from a given amount of reactant. But if I know that I want a desired amount of product, I can work backwards. I can work from product back to reactant, all because I can use a mole to mole ratio. So what do I need? This is where I want to do a nice review. Okay, back in Unit 1, or not Unit 1, Unit 7, we worked with mole island. So this is something that you should be nice and used to. All right, so atoms and particles on things island. We're still able to use the mole island exactly the same way. 1 mole equals the molar mass. 1 mole equals Avogadro's number, 6.02 times 10 to the 23rd. And then to go to liter island, remember that has to be liters of gas at STP. 1 mole is equal to 22.4 liters. Now, this is exactly the same thing that we've used in Unit 7. And so the one new piece that you need for stoichiometry is number 1. Sorry about that. Number 1, you have to have a balanced chemical equation. Okay? Have to have a balanced chemical equation. And in order to write a balanced chemical equation, you'll use all of your knowledge that you gained in Unit 6. Okay? Step number 2, in order to switch from one compound to another, you're going to use your mole to mole ratio. And that mole to mole ratio is going to come from the coefficients. So what I'm going to do is add to our mole island, sorry again for my slides, the mole to mole ratio, and I'll make a note that comes from the coefficients of the reaction. Oh, sorry. Okay, so I want to go ahead and work some problems with you all together. And I will mention this. All of the problems that I'm going to be working are going to be focusing on this section here of mole island, the gram to mole part. But if you're given a problem, and there's a couple of pages in your unit book that has practice problems where you can go from liters to moles and things to moles, that will never change. Just because of the example problems that I'm working aren't necessarily using those other two sections of our mole island doesn't mean that they won't be used eventually. Okay, so just keep your eyes open for things that you already know how to do. So open up to page 2 of your unit book, and I want to look at number 1 altogether, please. Number 1 says, given the following equation, so I have 2 butane plus 13 oxygen gas gives me 8 carbon dioxide and 10 waters. Show what the following molar ratios should be. So I'm going to write our equation out for us. So here's 2 butane, C4H10, plus 13 O2 produces 8 carbon dioxides and 10 waters. Okay, so that is a combustion reaction. You should be able to write and balance those. Now let's practice our new piece of knowledge. So I'm going to look at C4H10 to O2. Okay, so in order to find my molar ratio, I'm just going to look at my equation. So in front of butane, I see a 2. So there's the first part. In front of oxygen gas, I have a 13. And so my molar ratio is 2 to 13. All right, let's try one more all together. O2 to CO2. All right, when I look, I again see a 13 in front of my O2, and now in front of my carbon dioxide, I have an 8. So if you would, go ahead and pause the video, and you all try C, D, and E. Okay, so the molar ratio for oxygen gas to water is going to be 13 to 10. The molar ratio for butane to carbon dioxide is going to be 2 to 8. And the molar ratio for butane to water is going to be 2 to 10. So hopefully you recognize that both of these molar ratios could be reduced, 1 to 4 or 1 to 5. But the good news is if you didn't recognize that, you aren't going to get your problems wrong in the long run because of it. You can leave your molar ratios unsimplified or go ahead and simplify them. So let's work a problem. Let's look at number 2. Number 2 says, given the following equation, and I have 2 potassium chlorates, KClO3, decomposes to 2 potassium chlorides and 3 oxygen gases. So there's a decomposition reaction. It says how many moles of oxygen gas can be produced by letting 12 moles of KClO3 react. So when I label what I'm starting with and ending with, I have 12 moles to start with, and I'm ending with moles of oxygen gas. So I also like to label my chemical equation so that I can very obviously see that I'm switching my compounds. So 12 moles, sorry about that, 12 moles of KClO3, and I want moles of O2. So hopefully you can see KClO3 is not the same thing as oxygen gas. So the only way that I can change my compounds is by using a mole-to-mole ratio. So I'm going to go ahead and draw up the section of mole island that I'm interested in. Gram, mole, and mole. But I want you to see this problem didn't give me grams to start with. So I'm already starting here on mole island. And in order to get to moles of oxygen gas, I'm just going to use a mole-to-mole ratio. I don't have to leave mole island. I don't have to use the periodic table or Avogadro's number. All I need in this problem is just my mole-to-mole ratio. So 12, sorry about that. It's a little technical difficulties. 12 moles of KClO3. Moles of KClO3 to moles of O2. We're using our same skills that we perfected in Unit 7, setting up our fractions and canceling our units. Now, the only place that our conversion factors come from is the coefficients on our balanced equation. So I need a 3 and a 2. When you type this into your calculator, I like to hit the enter button several times just to make sure I'm not having any finger fumbles or any easy mistakes. So 12 times 3 divided by 2 is how I type it into my calculator. Or you can type it in as 12 times 3 halves and you'll get the same thing. But please always remember that your answer needs to have the correct number of significant figures as well as units. So 18.00 moles of oxygen. Now, you might be asking, how did you know that the 3 needed to go on top and the 2 on the bottom? Well, my giveaway is the fact of my compound labels that I have. So it's very, very important that you aren't just writing moles and moles, that you're actually being specific about what compounds we're working with. That will help you from making silly mistakes. Okay, so let's go on and look at number 3. Number 3 says, given the following equation, 2 potassium plus chlorine gas produces 2 potassium chloride. Okay, how many moles of KCl is produced from 2.5 grams of potassium and excess chlorine? So my problem gives me 2.50 grams of potassium, and it wants moles of KCl. So again, I have a good visual that shows me that I'm switching from one compound to another, and so I need a mole-to-mole ratio. So on this problem, I'm still starting with Mole Island, and I'm going to work my way. I'm starting on Gram Island this time with my grams of K. I'm going to work 2 moles to moles, and then I don't have to leave because that problem wants moles of KCl. So 2.50 grams of K, grams of potassium to moles of potassium, moles of potassium to moles of KCl. Okay, so when I fill in my conversion factors, this first one that I'm putting parentheses around is just a gram to mole conversion. So remember, 1 mole is equal to the molar mass. So that means that a 1 is going to go on top next to moles, and on the bottom is going to be 39.10 grams of potassium, and that comes from the periodic table. Now, my mole-to-mole ratio is going to be the only time that I have a number that's not 1 next to the unit mole. So look at my chemical formula. My mole-to-mole ratio is going to be 2/2. When you type this into your calculator, you can even recognize that 2/2 is the same thing as 1. And you don't necessarily have to multiply by it, but if you don't recognize it and you just like to type everything in your calculator, you will still get the same answer. And my answer with the correct number of sig figs in units, 0.0639 moles of potassium chloride. Sorry about that. My slide keeps switching. Okay, so let's all look at number 4 together. I'll help you get started, then I would like you to take a turn to set it up. So it says, given the following equation, so I have sodium oxide plus water produces 2 sodium hydroxides. And that's a good old synthesis problem. When I label what I'm given, I have 120 grams of Na2O, and I want moles of NaOH. So I hope that you see we have 2 different compounds starting and ending, so we have to use a mole-to-mole ratio. If you would, go ahead and pause the video so that you can take a turn setting up the problem on your own. Get as far as you possibly can. Don't be afraid of making mistakes. All right, so to start our problem off, I have 120 grams of Na2O. I'm going to convert from grams of Na2O to moles of Na2O, moles of Na2O to moles of sodium hydroxide, NaOH. Okay, so when I fill in my conversion factors, 1 mole over 62 grams of sodium oxide, and my mole-to-mole ratio is going to be 2/1. Sorry about that. I know that has to be frustrating to watch. So 120 divided by 62 multiplied by 2 with the correct number of sig figs, that would be 3.9 moles of NaOH. I only need 2 significant figures in my answer, 3.9, because 120 technically only has 2 significant figures. Hopefully you did very well on that one all by yourself. Now let's look at number 8. On number 8, it does not give you a balanced chemical equation this time. And it says, iron and carbon monoxide are produced in a blast furnace by the reaction of iron 3 oxide and coke, pure carbon. If 25 grams of pure iron 3 oxide is used, how many kilograms of iron can be produced? So the first thing I want to do is write and balance my chemical equation. So the first sentence says the iron and carbon monoxide are produced. So that's the right-hand side of my arrow. So I have Fe plus CO. And it says I'm reacting iron 3 oxide and coke. So iron 3 oxide is an ionic compound, so I need to crisscross my formulas. Fe plus 3, O minus 2. So that would give me Fe2O3. And then it tells me that coke is just a common name for pure carbon. So I write pure carbon with just a C. It does not need a subscript because it's not part of Brinkelhoff. So if you would, go ahead and pause the video and balance your equation. After balancing your equation, your coefficients should be 1, 3, 2, 3, in the order that I have them written on the board. So when I read my problem and see what I'm given and what the problem's asking me for, I'm given 25.0 kilograms of Fe2O3, and the problem wants me to calculate how many kilograms of iron can be produced. So there's my sign. I have Fe2O3, kilograms of iron. Those are 2 different compounds. I have to have a mole-to-mole ratio. So you should be asking yourself, but a kilogram is not the same thing as a gram. You're going to have an extra step in order to use your mole-to-mole island, your mole island. So I'm going to need to convert from kilograms to grams, then grams to mole, mole to mole, back to grams. So if you will, go ahead and pause your video. This problem is going to be a little bit longer than what we've worked on so far. So try to get as far as you possibly can. Okay, after setting up your problem, here's what it should look like. So 25.0, sorry about that, 25 kilograms of Fe2O3. Kilograms goes to the bottom to cancel, to grams of Fe2O3 on top. So again, notice how I'm labeling my compounds so I very obviously see what I'm working with. Grams of Fe2O3 to moles of Fe2O3. Moles of Fe2O3. So here's the big conversion from iron 3 oxide to iron. So here's moles of Fe. The only time that your compounds can change is when you have a mole-to-mole ratio. Now, I'm just going to go back to kilograms, but this time working with iron. Moles of Fe to grams of Fe. Grams of Fe to kilograms of Fe. Okay, when I fill in my fractions, this is how I work every stoichiometry problem. I make all of my fractions all the way across, then I go back in and fill in my conversion factors. I like to take things one step at a time. So there are 1,000 grams in a kilogram. 1 mole is the same as 159.7 grams of Fe2O3. My mole-to-mole ratio is 2 to 1. 2 to 1. 55.85 grams of iron to 1 mole of iron. And again, 1 kilogram is 1,000 grams. So if you recognize that I have 1,000 over 1 here and 1 over 1,000, those two cancel, so you don't technically have to write them in your balanced equation or type them into your calculator. So if you do, though, you'll still get the same exact answer. So the final answer with the correct number of sig figs is going to be 17.5 grams of Fe. All right, so that has been, 4 stoichiometry examples. And I want to address when do you need stoichiometry versus when can you use just a regular mole conversion. So if you will, turn to page 4 with me in your unit book. page number 4, and I want you to look at number 3. Number 3 says, laughing gas or nitrous oxide, then it gives you the chemical formula, is sometimes used as an anesthetic in dentistry. And so it gives you an equation. NH4NO3, so that's ammonium nitrate, decomposes, here's N2O, our nitrous oxide, and water. Now, it's a good habit to get into to verify that every equation you are given is balanced. So let's go ahead and do that. I have 2 nitrogens on the reactant side, 2 on the products. That looks good. When I look at my hydrogens, I have 4 hydrogens on the reactants, only 2 in the products, so I put a 2 in front. And then when I look at my oxygens, I have 3 as a reactant, 1, 2, 3 as a product, so my equation is balanced. When you read letter A, it says if 32.5 liters of N2O is in a dentist's office, assuming STP, how many grams of N2O or nitrous oxide are present? So again, I like to label just so I can see what I'm doing. 32.5 liters, and this time it wants grams. So I am working with the exact same compound. Because of that, I do not need a mole-to-mole ratio. This is just a mole-island conversion like we did all through Unit 7. So 32.5 liters of N2O, to moles of N2O, moles of N2O to grams of N2O. 1 mole is 22.4 liters, and 1 mole is going to be, if I can keep my slides from flipping back and forth, 44.02 grams. You guys can divide and multiply and get your final answer with sig figs. So what I want you to see is here, I did not need a mole-to-mole ratio because I worked within the same compound. Okay. All the other problems on page 4 are a mix. Some of them you only need mole island like we did in Unit 7. The rest are going to need your mole-to-mole ratio. So after watching me work some problems, it's time for you to practice. So you can either go back and finish page 2 and 3. You can finish page 4. You can finish page 5. If you are especially needing more practice, do them all. More practice never hurt anyone. But just make sure you're taking it one step at a time and using your mole-to-mole ratio and your mole island, your gram to mole conversions carefully. Thank you for watching and good luck.